So now that we have taken care of that, in this comprehensive series, we will dive deep into the YOLO11 algorithm, breaking down its code flow step by step. Using a debugger, we'll explore the intricacies of the code to see how each component functions. Whether you're new to AI or looking to elevate your computer vision skills, this playlist provides the knowledge and hands-on experience you need to understand and implement YOLO11's detection techniques. A special thank you to Glenn Jocher, founder and CEO of Ultralytics, and the entire Ultralytics team for their exceptional contributions to advancing the fields of computer vision and AI. This video wouldn't be possible without the foundational code developed by the Ultralytics team and the countless GitHub contributors and researchers who, over the years, have advanced previous versions of YOLO. Their efforts have enabled the algorithm to reach new heights in this latest YOLO11 version. Quick disclaimer, I have no ties to Ultralytics. I'm just genuinely grateful for their open source contributions, incredible work, thorough documentation, and ongoing community engagement. Ultralytics YOLO11 is a cutting-edge, state-of-the-art model that builds upon the success of previous YOLO versions and introduces new features and improvements to further boost performance and flexibility. YOLO11 is designed to be fast, accurate, and easy to use, making it an excellent choice for a wide range of object detection and tracking, instance segmentation, image classification, and pose estimation tasks. Again, welcome to the step-by-step guide to master Ultralytics YOLO11 for AI object detection. This is the companion Colab notebook to the YouTube video for hands-on practice and to run sections of code as you follow along with the video. The learning goals will be to understand the code flow and architecture, to apply AI object detection techniques through coding sessions, to gain confidence in working with AI algorithms by debugging and troubleshooting code, and to develop a strong foundational understanding of convolutional neural networks and their role in object detection. To get started, the first thing I want to do is show you how easy it is to use the Ultralytics package in a Colab environment. You can find the link to this Colab notebook in the video description. Naturally, our first step is to pip install the Ultralytics library. Once it's installed, we'll download, for example, this image of a Ford Explorer, which we'll use for our predictions. To download an image programmatically in Colab, just make sure it's in a direct image URL format, as you can see here. By the way, you don't have to use this specific image. You can use your own by replacing the image URL with one from your Google Drive. The code will still work. YOLO11 model introduces improved feature extraction, capturing details with even greater precision while using fewer parameters. It also processes faster, enhancing real-time performance. Here's how YOLO11 advances both speed and accuracy. Now we're going to start making a prediction. There are a few different ways to do this, and I'll show you the options. By the way, I'm including here the links to the Ultralytics documentation, which I consider a goldmine of information. The first two methods involve using the command line interface with the Ultralytics YOLO commands. The syntax looks like this: YOLO task mode arguments. Notice that task and even the arguments are optional, but mode is required. In this first example, we'll skip the task and simply use the mode along with a couple of arguments, specifically the model and source arguments. One reason we don't need to specify the task is that it's inferred automatically based on the mode and arguments provided. Also, since we're running YOLO_n.pt for the first time, you can see it being downloaded to our current folder on the left. Next, in the second example, we'll also use the command line interface, but this time we'll explicitly pass the detect task. We'll get the same result as before, since again, task is optional. Another common approach is to run it directly as a Python script, as shown here. Simply import YOLO from Ultralytics, then specify the model and source to run the inference on. Another option is to run model predict, which also accepts multiple arguments that can override defaults at inference time. Model predict also provides additional output details, including the actual results object. This contains information on detected bounding boxes, labels, the original image, and speed metrics. This can be especially useful if you need deeper insights into the detection process or want to further analyze outputs programmatically. Now, for this specific Explorer image, I wanted to see how different model sizes would score on the confidence value. The general expectation is that larger models will score higher, but also take longer to make predictions. So I ran each model on this same image. However, I noticed that inference times, even with the same model and identical parameters, varied slightly. In the smaller models, these variations are just a few milliseconds, but in the larger models, they can reach fractions of a second. To get a more reliable average inference time for each model size, I created a script that runs each model architecture 10 times, then plots both the average confidence score and inference time in milliseconds. As you can see, the end-to-end times vary slightly between runs, and this isn't just for inference time. We're also seeing slightly differences in image pre-processing and results post-processing. After running 10 predictions on each model, here's the freshly generated plot showing the results. As expected, the smaller models are faster. On the CPU-only resources provided by Colab, the nano model performs inferences in around a quarter of a second, while the extra-large model takes about 3 seconds. Of course, these results are slower than the benchmark scores we'd expect on the COCO dataset using A24 TensorRT10 NVIDIA GPU with half floating precision. Still, there are some interesting observations from these predictions. The small model performs noticeably better than the nano model, and it's still very fast, around half a second per inference. The medium model does show a slight improvement, but it also takes significantly more time. Surprisingly, the large model actually outperforms the extra-large model in both the speed and confidence. It runs in half the time and achieves better confidence, despite having only half the number of neural network parameters. In this step-by-step video, we'll focus on the nano model as it offers fast and reliable predictions, making it ideal for applications that require quick inference without demanding significant hardware. Up to this point, we have only been using our Colab environment. Since we're also going to leverage our IDE, preferably VS Code, we'll need to download the GitHub code locally. To do this, follow the steps shown here in the documentation to clone the Ultralytics repository and start experimenting with the latest source code. Once it's cloned, navigate into the directory. If you're considering contributing to development in the future, you can install the package in editable mode using the -e option as shown here. Otherwise, if that's not your goal, simply leave out the -e. So go ahead and complete these steps and continue with the video once you're done. I strongly believe the learning experience will be much greater if you follow along with your VS Code setup. All right, once you've done that, navigate to the Ultralytics folder where you downloaded the repo. I renamed mine to Ultralytics_dev, but feel free to leave yours as Ultralytics. Next, let's download our Explorer image. The image URL is in the video description. After downloading, copy the image from your downloads folder into the Ultralytics folder as shown here. We now have the image locally. This specific RGB JPEG image has a resolution of 1024 by 768 pixels, width and height respectively. Okay, we're almost ready. Go ahead and launch VS Code or your IDE of choice. In the top menu, go to File, Open Folder, and select the recently downloaded Ultralytics folder. Next, create a basic Python script as shown here. I named mine YOLO11.py, but feel free to choose any name you like. Save the script, and on the first line, where it says from Ultralytics import YOLO, go ahead and add a debug breakpoint.